Hi, welcome to the third video of this mini-series where I explain the research that I've done so far. And this video is on my PhD project, which is on zebra finches, so birds, and how they see depth. Zebra finches like to fly into the crowns of trees, and clearly what they want to do is avoid flying into the tree or flying again or colliding with other birds. So the problem that they have is that they cannot use stereo vision for depth perception. So the reason for that is that other than, for example, in the human head or in the head of other animals with forward-facing eyes that use depth perception a lot, the eyes are too close together, and they're also directed to the sides, which means that the part where the vision overlaps is very small, and it only works in a very close distance. So for pigeons, there is actually behavioral data on this, and they only can use their stereo vision for about 15 centimeters. And the zebra finches are much smaller than pigeons, which means that their stereo vision probably only reaches a couple of centimeters. So how do they see in depth? Well, there are other animals that face the same problem, which are even smaller, and that are flying insects. And our collaborators were working on blowflies at that time on that kind of topic. And the idea is that these animals use optic flow. So the motion of the image on the retina while you're moving through an environment to estimate depth to objects and to get an idea of the 3D composition of the environment. So basically what you can imagine optic flow, how it works, is that you don't compare images of the two eyes, but you compare images of two time points where the image is taken from slightly different positions in space. And that works best if you're moving in a straight line. So that's when you get most of the depth information in your optic flow. If you make a movement with the head like this, then there is basically no depth information in the movement. If you move in a straight line, then you get depth perception, and you can see that in insects, in flying insects, that they tend to move in straight lines rather than fly in like smoother curves. And that's exactly because, and the idea is that that's because they want to get depth information from this movement. So we were interested in whether the birds also do have a similar strategy in gaze. And what we did was build a flight arena which had halfway a wall that they had to fly around. So if they wanted to get from one point in the arena to the opposite side, they would have to fly around that wall, which means they would be forced to fly in a curve. And as we said, a curve is not good for depth perception in that moment. So we had the birds fly in this smooth curve, and we wanted to know whether they still do something to their gaze. So we were looking at the orientation of the head while they were flying in that curve, and what we found was that the bird would hold the head in a constant angle compared to the world. So not compared to the body, but to the world, which means that the head wasn't doing the same smooth flight, basically, that the body would do, but it would try to avoid the optic flow from this rotation movement and to clean it up so that that the eyes would mostly see the optic flow from the translation, so the straight movement. So we think that that's a hint that the birds also use optic flow for depth perception. And that again was followed up with an electrophysiology study where the animals were anesthetized, and we then put them into an LED monitor, which was pretty big, and that was like a spherical, almost spherical monitor. We could play videos on this monitor, so you can basically, it's basically, how do you say it? It's more or less like a virtual reality thing, where you have a surround monitor, and then we played a reconstruction of the movies from the real flight in the bird. So again, we had the trajectories of the birds flying through the arena, and we had the head movements. And then we could take this movement information and place it in a computer model of the arena. And from this, we created these videos that were displayed on these more or less spherical monitors. So while the animal was anesthetized and inside of this monitor, we could do electrophysiology and record the response of the neurons to these flights, which was pretty hard to do, I must say. And we got some interesting clues out of that, but because it was the first study in that direction, it was more of an opening of a possible field. So that was my graduate thesis. Yeah, you were asking about magnetoreception in the birds. And indeed, while I was a graduate student in the same lab, there was a postdoc who was working on magnetoreception in the zebra finches. And he found that they are able to do it, but they cannot tell all four directions, so northeast, southwest. They could only know whether it's on a south, in the north axis, or on the east-west axis, if I remember that correctly. So they do have a magnetic compass. That's correct. So it gives you a sense of direction, but it doesn't allow you to fly around an obstacle in your environment. You need vision for that. Okay, thanks for watching. Don't forget to subscribe and give me a like, and see you in the next video. Have a nice day. Bye bye.